You are listening to The Vocal Technologist. Spoken tech for your ears.
Usually when we talk about growth, there's this expectation of a natural, manageable curve, like planting a tree.
Right, yeah.
You give it water, you
Yeah,
give it
yeah.
time, and year by year, it just sort of slowly branches out. You can sit back and just watch it happen.
Because it's biological. I mean, it's predictable. You kind of expect the roots to grow at roughly the same pace as the leaves.
Yeah.
You definitely don't expect the tree to suddenly, rewrite its own DNA.
Exactly. But then you look at what's happening in the tech landscape right now, right around mid-April 2026 here, and suddenly that tree isn't just growing, it's mutating.
Oh, completely mutating.
It's ripping up the concrete, basically demanding the electrical output of a small country just to keep going. We're looking at a landscape of extreme pressure. And today, we have a really fascinating stack of sources curated specifically for you, pulling from some of the top tech newsletters and industry reports out there.
It's a great stack today.
Yeah, we are diving into these.
Yeah, the structure of that deal tells you basically everything you need to know about the current urgency in the market. It's $5 billion up front, with up to $20 billion more tied to specific commercial milestones.
Right.
And the commitment goes both ways, too. Anthropic is committing to spend more than $100 billion on Amazon Web Services over the next 10 years.
Wow.
But the number that truly dictates where the industry is heading is the power requirement. Anthropic has secured up to 5 gigawatts of capacity for training and deploying its models.
Wait, 5 gigawatts. Let me just make sure I understand the physical scale of that. A single gigawatt is roughly enough to power a medium-sized city, right?
Yeah, pretty much.
So we are talking about dedicating the energy equivalent of a major metropolis just to train and deploy these AI models. Why is so much literal physical power necessary right now?
Because that power is fueling a fundamental change in how software itself is built. I mean, we're seeing a complete acceleration in developer velocity. Take Cloudflare as an example from our sources. 93% of their R&D organization is now using internal AI coding tools.
93%. That's almost everybody.
Basically, yeah. But they didn't just, buy a generic off-the-shelf product. They built their own AI infrastructure on their own platform using what are called custom MCP servers and specific access layers.
Okay, if you're listening to this and wondering what on earth an MCP server is, let's break that down. Model Context Protocol, or MCP, is essentially a standardized way for AI assistants to securely connect to a company's private data. Because if you just give an AI access to your entire code base, that is a massive security risk.
Oh, absolutely. A huge risk.
Right. So developers build these MCP servers to act as controlled gateways, letting the AI read specific internal tools and databases without exposing the whole system.
Precisely. And by integrating AI so deeply and securely into their proprietary systems, Cloudflare completely changed their output. Their 4-week rolling average of merge requests, which is basically the number of times developers are pushing new completed code into the main system, that spikes from around 5,600 per week to over 8,700.
That is a staggering jump in pure output. And the stack notes that it isn't just writing code, right? Testing the code is accelerating just as fast.
Oh, yeah.
Tools like QA Wolf are getting engineering teams to 80% automated end-to-end test coverage. They're reducing quality assurance cycles from hours down to literal minutes. Like Drata's team of 80-plus engineers achieved 86% faster QA cycles and produced 4 times more test cases.
It's wild, a traditional bottleneck of software engineering, waiting to see if the thing you built actually works without breaking everything else. It's just evaporating.
Yeah, even database querying is changing.
Yeah.
The SAC mentions this tool called GGSQL that allows developers to write queries combining SQL data retrieval with visual specifications in a single syntax.
Right.
You don't pull the data and then separately figure out how to graph it. It happens simultaneously.
Which, of course, leads to an inevitable problem.
Yeah.
You can't just increase the velocity of an entire global industry without breaking something. The ecosystem is straining under this hypergrowth. I mean, GitHub had to entirely halt new signups for their Copilot Pro Plus Wire, and student plans.
Just halted them entirely.
Right.
When a Microsoft-owned entity has to pause sign-ins for its flagship developer tool, that tells me the demand for AI assistance has officially outstripped the physical infrastructure's ability to provide it. The compute costs are just soaring way too fast.
Yeah, and it's causing panic at the highest levels, too. According to the reports, engineers at Google DeepMind are actively using Anthropic's Claude as a daily tool because the rest of Google's internal tools just aren't keeping up.
Wait, really? Google engineers are using Anthropic's tools?
Yep. Google is having to form a dedicated elite team of researchers and engineers just to sharpen the coding capabilities of its Gemini models to, close the gap with Anthropic.
It feels like the industry is a Formula One team trying to swap out the engine while the car is currently doing 200 miles an hour down the straightaway.
What's fascinating here is the collision between infinite software potential and finite physical reality. You can write software infinitely fast, but eventually it has to be processed by a silicon chip housed in a server rack, pulling electricity from a grid. The software acceleration is slamming into a hardware bottleneck.
Which brings us to a massive structural shift happening at the world's biggest hardware company. Because, like you said, all this AI code still has to live on physical devices in our pockets and on our desks. Apple is making a generational executive move. After a 25-year career at the company, John Ternus is taking over as Apple's new CEO on September 1st, while Tim Cook transitions to executive chairman.
And the background of the incoming CEO is the critical detail here. Ternus is a mechanical engineer by trade. He most recently led hardware engineering for all of Apple's products.
Oh, wow.
Yeah, this is a total re-engineering of how Apple builds things to manage the exact physical bottlenecks we just discussed. Apple is aggressively restructuring its newly combined hardware engineering and hardware technologies division.
Right, they were organizing it into 5 key areas under Johnny Srouji. That's hardware engineering, silicon advanced technologies, platform architecture, and project management. But how does a company manage that level of parallel complexity when all those separate silos have to eventually come together into a single iPhone or Mac?
Well, we can actually look back at how developers handle complexity in software to understand what Apple is trying to do in hardware. In the programming world, when you have mass amounts of parallel work happening, developers use something called jujitsu mega merges.
Jujitsu mega merges.
I
Love the name, but how does that actually function in practice?
Think of it like constructing a massive skyscraper. You have electricians, plumbers, and drywall installers all working on different floors at the exact same time. If they only look at their own blueprints, the plumber might run a pipe right through where the electrician planned to put a main breaker box. So a jujitsu mega merge is essentially a master blueprint overlay. It lets developers view many different streams of code simultaneously to see the whole picture of how these parallel branches might interact.
So they aren't actually combining the code permanently yet. They're just like overlaying the blueprints to spot collisions before the building is constructed.
Exactly.
The stack mentions that these mega merges aren't meant to be pushed to the remote main server. Like, branches are still published individually.
Correct. The mega merge just gives them the overarching vision to ensure the chaotic parallel streams don't conflict. And Apple is applying that exact concept to physical engineering. They need hardware engineering, silicon design, and platform architecture moving at maximum speed on parallel tracks. But they need a tightly managed mega-merge view at the executive level to ensure the AI silicon interacts perfectly with the hardware architecture before the product is ever assembled.
So what does this all mean? Because I had to push back on this Apple news for a second. With John Ternus, who is a pure hardware guy, taking the reins right when companies like Anthropic and OpenAI are defining the future almost entirely through software, is Apple risking becoming just a dumb vessel for other people's AI? Or is this proof that whoever controls the physical hardware, the actual glass and metal we touch, ultimately holds the power?
Controlling the physical layer, the device itself, gives you the ultimate distribution channel. But as these tech giants grow to manage both the hardware in our hands and the software running our lives, they invite entirely new types of friction. When you control the physical layer, you hit regulatory walls and physical ceilings that software companies simply don't face in the same way.
We are definitely seeing that friction intensify in the legal realm. I mean, California is actively suing Amazon for antitrust violations, specifically alleging price fixing. Looking at the filings ahead of next year's trial, the lawsuit claims that Amazon punished sellers for offering lower prices on other websites and pressured major brands to make competing retailers raise their prices.
Right.
Now, obviously, these are allegations that will be debated in court, but it highlights the immense scrutiny placed on these scaling monopolies. And it's happening internationally, too. The European Union just passed a law requiring that future phones must have batteries that can be easily changed by users at home using basic tools.
And that regulation strikes at the very core of tightly sealed ecosystems like Apple's. It forces a reorganization of the hardware design philosophy from the outside in.
Totally.
And the friction is only going to increase as AI gets more capable. Elad Gil recently published some thoughts on the AI frontier, predicting a massive percentage of GDP will be attributed to AI revenue by 2030. But he also anticipates a severe societal blowback.
Yeah, he predicts a major rise in anti-AI regulation. And even more startlingly, he anticipates an increase in actual physical violence against the technology itself as societal friction grows. It's a wild juxtaposition.
It really is.
On one hand, the economic incentives are astronomical. We have a source here showing the newsletter TLDR is hiring an applied AI engineer for up to $350,000 a year just to make internal workflows composable. Developers are flocking to events like Microsoft Build 2026 in San Francisco this June just to learn from teams scaling the next generation of AI. But on the other hand, we are anticipating people taking baseball bats to AI servers out of societal frustration.
Which exposes a fascinating vulnerability in these scaling systems. We worry deeply about physical vulnerabilities, the baseball bats, the regulatory lawsuits, the power grid limitations. But what about the digital vulnerabilities?
Oh, this brings up the quantum computing fear mentioned in our stack. There is this pervasive anxiety that once quantum computers reach a certain level of power, all of our encryption will be instantly broken. Like all our private data, our passwords, our banking info will be totally exposed.
Right, that's the narrative.
But the experts in our sources say this technological anxiety is completely misdirected. Quantum computers are actually not a threat to 128-bit symmetric keys.
If we connect this to the bigger picture, the panic entirely stems from a mathematical misunderstanding of how different types of encryption work. We have asymmetric keys, like public key cryptography, and symmetric keys. Asymmetric encryption uses two different keys, one public and one private, relying on the difficulty of factoring massive prime numbers.
Okay.
Quantum algorithms, specifically Shor's algorithm, are exceptionally good at factoring those numbers. So yes, asymmetric cryptography is vulnerable.
But both AES-128 and SHA-256, which are the foundational building blocks of modern secure communication, are symmetric keys. They use a single shared key.
Why doesn't a quantum computer just slice through a symmetric key the same way?
Because people misunderstand a specific quantum tool called Grover's algorithm. They assume Grover's algorithm will instantly solve the symmetric key puzzle. But Grover's algorithm doesn't solve the puzzle. It basically just speeds up the process of brute forcing it. Specifically, it roughly halves the effective bit length of the key. Let me make sure I'm following the math here. A 128-bit key means there are 2 to the power of 128 possible combinations. Grover's algorithm halves that effectiveness, meaning a quantum computer only has to search 2 to the power of 64 combinations.
Exactly. But 2 to the power of 64 is still 18 quintillion operations.
18 quintillion.
Yeah. Even for an advanced quantum computer, performing 18 quintillion operations sequentially is practically impossible within a reasonable time frame. The math simply doesn't support the panic. AES-128 remains secure. No symmetric key sizes have to change as part of the post-quantum transition.
It's so ironic. We're absolutely terrified of quantum computers breaking our passwords, which turns out to be a mathematical myth. Meanwhile, we struggle to scale our own software without crashing GitHub, and our hardware giants are facing lawsuits and battery regulations at every turn. We really struggle to build complex systems that scale gracefully.
We do. Our code breaks, our servers overheat, our societies rebel. But if we want to see a flawless, frictionless system that doesn't buckle under scale, regulation, or power constraints, we actually have to look backward. Way backward.
Oh, I like where this is going.
We have to look at the original engineers. Bacteria. Biology has been quietly reorganizing complex systems at scale for billions of years.
I have been waiting to talk about this part of the stack. It's the story of Howard Berg. In the early 1970s, Berg set out to apply his training in pure physics to understand how bacteria move. Which sounds simple, right?
You'd think so.
But bacteria move so fast relative to their size that traditional observation was impossible. Berg literally had to invent and build a totally new automatic tracking microscope just to keep a single bacterium in his field of view. He had to build the tools of observation before he could even begin to ask the question.
He needed to build his own lens, and what he found when he finally observed them was the flagellar motor.
What exactly is the flagellar motor, and how does it actually function?
It's a microscopic biological engine that spins the tail-like appendage of the bacteria to propel it forward. And its mechanics are astonishing. It operates remarkably like an electric motor built by humans, complete with a rotor that spins and a stator that remains stationary. But instead of running on electricity from a wall outlet, it runs on a proton gradient.
A proton gradient. So imagine a microscopic hydroelectric dam. But instead of water flowing over a turbine to generate power, it's a flow of hydrogen ions, or protons, rushing through channels in the motor. The physical flow of those protons forces the rotor to turn.
That is a perfect analogy. The chemical gradient physically turns biology's wheels, and it operates at near 100% efficiency. Think about Anthropic needing a 5-gigawatt power plant to run their AI models. Berg was analyzing biological engines that scale infinitely, replicate flawlessly, and run on mere chemical gradients.
Bacteria were essentially the original autonomous vehicles, and Berg was reverse engineering their tiny 5-gigawatt engines with 1970s tools. And the most remarkable part of Berg's story isn't just the tracking microscope, it's his foresight. He hypothesized this exact physical mechanism, the proton gradient, the rotor, the stator, a full 50 years before scientists definitively discovered and proved how it actually worked on a molecular level.
Wow.
He was half a century ahead of the technology required to prove his own theory.
This raises an important question about how we approach complex systems today. Whether it's Apple fundamentally restructuring its silicon teams to prepare for the next decade, or Amazon pouring $25 billion into a 5-gigawatt AI infrastructure, or physicists in the 1970s building a custom microscope to track bacteria. I mean, the core process of innovation is identical. You have to step back. You have to build a new lens to see the whole picture.
Sometimes that lens is a physical tracking microscope. Sometimes that lens is a jujitsu megamerge that lets you overlay the blueprints of your code. You have to build the lens to figure out how the motor actually works under extreme pressure. Here's where it gets really interesting. We are living through a moment where the lenses are building themselves.
Yeah, that's exactly it.
AI tools are writing their own code. We are accelerating our research capabilities at a speed that Howard Berg couldn't have possibly imagined in the 1970s. We have covered a massive amount of ground today.
We truly have. We started with the immense scale of the AI arms race. Amazon's $25 billion investment, Anthropic securing 5 gigawatts of power, and developer merge requests skyrocketing thanks to tools like QA Wolf and internal MCP servers at Cloudflare. We saw the breaking points with GitHub pausing Copilot signups and Google scrambling to close the coding gap.
From there, we looked at how hardware giants are adapting, with Apple's new mechanical engineer CEO taking the helm and Johnny Srouji reorganizing the hardware division to manage complexity, much like a mega-merge in software. We looked at the friction of Scale California's antitrust lawsuit against Amazon, the EU forcing swappable phone batteries, and the grim predictions of anti-AI regulation and physical blowback.
We broke down the mechanics of cryptographic security, exploring why AES 128 symmetric keys remain mathematically safe from Grover's algorithm. And finally, we zoomed all the way in on Howard Berg's 50-year quest to understand the proton-driven hardware of the bacterial motor. And the key takeaway for you listening right now is that whether you're a software developer trying to survive this massive surge in AI-generated code, or you're a consumer swapping out your phone battery on your kitchen table because of a new EU law, you are living inside these massive scaling systems.
You are part of the reorganization. This leaves us with one final thought to mull over. Howard Berg spent 50 years waiting for the physical technology of the world to catch up to his hypothesis about the bacterial motor. With AI now writing its own code, testing its own boundaries, and accelerating our research capabilities to unprecedented speeds, we have to ask, what 50-year mysteries are we about to solve next Tuesday? And more importantly, are we ready for the answers? Thank you for joining us on this deep dive. Keep questioning the systems around you.
Spoken Tech, for your ears.